This is kind of like one of the questions that probably anyone who ever like worked with Kafka need to answer for themselves, but also like answer to people in community. So what do you should choose? What do you choose with? You go with Flink or you go with Kafka Streams? And Flink has a squirrel logo. Kafka Streams has an otter logo. So we have an epic battle between otter and squirrel. My name is Viktor Gamov. I work as a principal developer advocate at a company called Confluent, founded by original creators of Apache Kafka. We're running Kafka as a service. I wrote a book about Kafka, know a few things about this, called Kafka in Action. I'm a Java champion, so expect a lot of jokes for Scala people. Any Scala people here, by the way? Someone mentioned. Okay. So, question to you, Scala people. Why Scala developer lost in forest? Because they kept following traits and forgot their way back to object. See, I can prepare. You know, my second that needs to be on my resume, kind of like I'm making fun of the Scala people. Anyway, so stream processing. Stream processing is the process of dealing with events as they arrive, as they're flowing into system. That's it. And we're going to be covering this subject from perspective of two tools. It's a tool set, meaning that there should be either framework, library, or some custom code that you were writing in order to process stream of infinite data. This is the general term, but all my examples will be around Kafka. Some of the things applicable other systems. If I will be talking about certain things about Flink, you can do Flink with other streaming sources like Pulsar. You can do this with the Kinesis, but for all this and the purposes of this particular presentation, we're going to only focus on Kafka. But you know, I don't want to create this impression that the stream processing equals Kafka. Yes, in many cases it is. Kafka is. Anyone running like alternative solution? By the way, like I'm thinking that Kafka is the, you know, one and only solution. But maybe some Pulsar folks here. No, great. That's fantastic. That's fantastic. So let me jump through some of the Kafka aspects that might not be relevant for our conversation, specifically like this one. I really like this slide. When I was talking that to folks about this presentation, I said this presentation doesn't have any AI. It's a solely data engineering, like streaming data engineering talk. And I was like, hey, this is the AI. Yes, this is the AI. And this is the picture that I used to explain a very important concept. Like these cute birds will help me to explain very important technical concept. Because many of you know that the way how Kafka usually, you know, applications that work with Kafka, stream processing applications, they're working through the cycle consume, process, and produce. And the consumption process is the most important because this is how data gets into stream processor. Would be Kafka Streams, or it would be Flink, or whatever. This data needs to land from the Kafka somehow. And the low level is the consumers. We scale our consumption by increasing numbers of partitions in Kafka topics and number in consumers in consumer group. Consumer group coordinator, this is the brain of these operations because that's why they're small and dumb, because they're not talking to each other. They don't know anything. It's a shared nothing architecture. So that's why consumer group coordinator, Mummy Bird, is responsible for assigning partitions to those consumers. It is very important because a framework like Kafka Streams that has very intimate connection to Kafka, it will use the same model in order to distribute work across instances of a Kafka Streams application. So that's from consumer side of things, and that's probably would be most important. Another thing that I like to mention that if you kind of maybe less experience on these things, Kafka is your source of truth. Data is there, so you can run multiple different examples on top of the Kafka data, multiple different use cases on top of the Kafka data. What means that you can run stateless stream processing, meaning that simple transformations, filtering, all the operations that will not require some memory of the past in terms of like what happened. And stateful stream processor, where you need to know what happened on the step back. You're doing aggregation, you're doing a window, you're trying to calculate running average on top of the 5-minute window. So you need to somewhere this data be persisted before runs until the new data will arrive. So that's the difference. So, but I like to use the analogy that on top of the same the chunk or same view of data, we can run multiple different use cases, and those use cases will be running in parallel. They might have a different scalability option. You can run these 2 use cases. One use case will be written in Kafka Streams, another use case will be written in Flink, and so far so on. That's the Kafka part. So I'm going to start explaining these 2 things or comparing 2 things like a Flink and Kafka Streams with approach of explaining how the application looks like. Anyone is like actually writing code, writing Java code, Kotlin code, Python code, or we have like a data engineers. That's interesting because if you're writing lots of Python code, this might be not very super relevant. However, there's a Python framework for Kafka Streams, like similar Kafka Streams called Faust, that was developed based and highly inspired by the way how the Kafka Streams application works. So let's talk about Kafka Streams architecture, so we can see how things are working. In the very beginning, everything starts with Kafka. Everything starts with Kafka. Kafka would be our storage. All the input data will come from Kafka topic. Kafka Streams is designed, is purposely built in order to work with Kafka topics. So that's why there is a even name. Name implies. Inside my application. So when I run in Kafka Streams application, it is a library. So I'm writing my Java application. It's a jar that sits in the class path of this application, and that's it. You can deploy this as you want. You can just run this as a public static void main application. You can run this as a microservice inside some sort of Spring Boot application or Quarkus application or Micronaut application or something like that. And this library actually does a lot. It does a lot from perspective of providing APIs, 2 typos or 2 flavors of APIs. One flavor that would look very much familiar for Java developers. It's very similar or highly inspired by standard Java library with Java util streams. Second type of API is more low level that allows to go deeper into application topologies and see how things are working. Kafka Streams is also stateful stream processing application library that allows you to perform stateful stream processing. So it means that Kafka Streams provides the machinery to handle state very efficiently. So it has some of the default implementation of state stores that would be used in embedded databases like RocksDB. And there's ability to, since it's running inside of JVM, inside of Java application, you have ability to fine-tune how this processing will be executed, have a control over runtime, what's the thread pool model, how many tasks per threads, and all this kind of cool stuff that people who optimize in performance love. Now, let's talk now. Let me quickly show you code before we're jumping into Flink. And if I go again, this is my GitHub where you can find this code. It's called Stream Processing Comparison. If you again wants to take a look at the code, you can find everything is here. It's a true or not true for Java 21, Flink 120, and Apache Kafka 3.9. So if I will show you my Kafka Streams application, the way how it looks like, usually I'm building, is it big enough? Let's see, zoom. Let's go a little bit bigger. Yeah. So there's a couple of things. What are we doing? So the model, what we use to design this type of applications, is based on the concept of direct acyclic graph. Pretty much every data processing system these days using some sort of like a way implementing this concept. So you have a source where the data comes from, you have a bunch of operators where this data go through, and there will be some sort of transformations, and there will be sync. In Kafka Streams case, it is very explicit, and it's always Kafka topics. In some cases, it can be state store. So when I am, where's my code that invokes this topology. So we're building topology and we're starting Kafka Streams application, and this is where this topology will be executed inside this runtime. When I need to read the data from Kafka topic, I'm using this method called stream. I'm specifying topic name, and now we do have a Java or like JVM rather representation of messages that goes in Kafka topic. So in Kafka, all our messages will have a key and will have a value. So that's why the API for building this application follows same approach. We have a key value pairs as our the elements of our stream. We can do this is example of stateless stream processing because it performs like mapping operation. So it does some sort of transformation. In this particular case, it reads the strings from Kafka topic and turn it into JSON objects. Because we need to take this JSON object and turn it to a Java object so we can do interesting things with this application. And after that, next step, you see it's kind of like a cascade of operations, and even my IDE can highlight top level operation map values, and after that, next step would be filtering. So we read the string, we turn it into Java object. After that, we're filtering based on if value is valid. And after that, we don't know if our messages came into topic in a proper partitioning scheme or a proper keying scheme. So we will also selecting topic. What the Kafka Streams will do, Kafka Streams actually will create additional repartition topic where it will collect all these messages from initial stream with a proper key. So in this particular case, I'm tracking flight delays, and I'm using particular route would that be unique, that will represent multiple combination between flight ID, origin, and destination. And I can say that this is something that I want to track, but based on the route key, I will be able to perform my analytics for figuring out what our flights are delaying and how I can track them. This is the totally kind of like a stateless build. We don't need to use anything in order to collect. Now, in another step where we need to do something with this data. So in this particular case, we are collecting some of the stats. Based on the static some of the information that comes from the stream, we need to have a point in time some entity where we can know what's the current status. So that's why instead of stream, we're using concept of table. So stream, if you think about this, it's your list of, it's a ledger, like all transactions that happen on your banking account. Whereas a table in this case would be the current balance, like how much money you have. So when you have a new transaction that happened on your credit card, your stream processor will recalculate your balance, and the result you will get after you're receiving the new transaction data. So in this particular case, we are trying to extract. In this particular case, we are getting a key and aggregating the data based on particular route key in one place, in one stats table. In another table, we are Kafka Streams provides the ways how we can also do like fan out based on certain condition, based on certain predicate. We can build some sort of routing. If it's X, we go into the one topic. If it's Y, it goes to another topic. Say, for example, based on the information that we collected through statistics of analyzing all these events, we can say that if this particular route considers a high risk, if it's high risk, we need to send topic that will be raised some sort of alerts. The results needs to be sent into, where's the final topic? Results of this processing will be sent into two topics. One will have a statistics of these flights, and another topic will have alerts. The cool thing about the Kafka Streams in this particular case, when I am not quite understand like what is going on here, I can always do one cool thing. If it allows me to do, I say I have a some of the things. So Kafka Streams comes with some cool, where's the, and generate stats. For example, let's take this one. We do have blah, 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 where we're building topology. We're building topology for this topology setup. And in the end, I can do topology and describe, and I can do write this into console. And when I run this, I can, first of all, it also comes with a testing framework that will not require you to interact with Kafka at any point. So that's very good for very small things like unit tests. It was super fast, and now I need to find the, So when I'm building this topology, I actually can get the textual representation of this topology. So I can do stuff like this. Let me try to see if I can copy this thingy. No, I cannot move, can I? Let me move this. So see, this is the actual application topology. So what I can do, I just go copy, go to Google, say Kafka Streams topology visualizer, and get something like there's a bunch of different projects, and I think this one is the right one because it does a very nice thing. So I can take this text based in here, and now I can do a view of this topology. Can you do this? Can you? No? It's broken? I think so. I think I copied everything. Yeah, should be. Looks like it. Let me do it one more time. Can I do this? Maybe application is broken, so you never know. Like live coding on stage, picking up link from the random links from the from internet. Yeah, for example, this is the oldie but goodie. This was initial first implementation of this use case. So essentially, this is a full-blown visualization of how the data comes from flight states. It's not. So we do have a flight status topic. We do some sort of transformations. We do repartition that will create additional topic that will be available in Kafka. And after that, we do have branches, so we can split two streams, and we can generate delays and alerts.
Good thing you name all those so it's readable.
Oh yeah, of course. So when you define, that's a good point. When you're defining this topology here, for example, I'm building this topology. Every component can get its own kind of like a naming and all these kind of things. Yeah, that's a good point. Super nice, built in. You don't need to do anything else. This is just a jar in your application. So this is how it feels programming Kafka Streams application. Now let's take a look on the Flink side of things. Now Flink, even though many times or like the many users use Flink together with Kafka, and it's quite popular use case, Flink is general purpose framework, that general purpose stateful string processing framework, meaning that it is, even though it can read data from Kafka, but data can be delivered from any type of sources. It can be files, can be some sort of custom source, it can be streaming source, it can be the batch source. If we need to interact with Iceberg, for example, there would be Iceberg connector that will be connecting to Iceberg to bring data inside the Flink. And this is also true for another way around. If we need to, when we process this data, in Kafka Streams, only option you have, data needs to land inside the Kafka. In Flink, it's not the case. Data can go data not necessarily needs to go anywhere at all. You can just writing this into console in whatever. You don't have to even have a sink in the Flink application. But there's a sinks for Kafka, GFS, also for Iceberg, as we learned today, that's how the data comes into Flink. Since it is a distributed stream processing framework, it applies with the cluster architecture. It has a few components that will run as a part of your cluster when you're running Flink. So we have a job manager that will be my application, my client application code will be interacting when I'm writing my Java topology or writing like a SQL. It will land into job manager that will turn into something that will be distributed to task managers. That's the workhorses of this thing. So these task managers will be receiving the instance of one of the jobs, and jobs will be executed inside the actual unit of work that will be running inside the task manager called the task slots. The task slots will start interacting with actual sources based on certain strategies. So for that matter, Flink is Flink architecture is more familiar for people who use Spark, people who use Hadoop before. It's a cluster-based architecture. You submitting jobs running there. You need to also figure out how you're going to be manage the resources for those computational bits. Talk a little bit about this. Let me show you how Flink application would look like. I was trying to also follow same use case, so you can have a comparison, as my friend and colleague Bill Bijek likes to say, apple and oranges, even though same use case would be implemented there. We will talking about the processor. So let's take a look. So our application, again, also starts with public static void main. But in this particular case, this application will not be running your code. It will be talking to a Flink cluster that will be retrieved from this from get execution environment. This is how we can connect to our Flink cluster. I don't have it here, but I think I have it somewhere else. Like if you want to run Flink, say locally, to emulate like network capabilities, you will do something like this. You'll have a Docker compose, for example, with a bunch of different containers. Say there's Kafka, where's my Flink? Yeah, so it will have an additional service for job manager. We'll have a task manager. Inside the task manager, we need to provide configuration. In this particular case, each task manager will have the instance of task manager will be scale 1, and each of them will have a 16 task slots. When I will be running this, if I will be running this from here, it will start embedded mode where the Flink job manager will be running inside my application. Because here I'm just getting some execution environment without connecting to anything else. And since, like I already mentioned, Flink is a general purpose, you need to use like specific APIs in order to interact with Kafka. So in this particular case, I'm using Kafka source. It is comes with special library that is maintained separately from the Flink, here I will configure connection to relevant pieces of my Kafka cluster. I'm setting a topic, I'm setting the group ID for my consumer. I can define where I want to start. So the offset management also support and handled. And now we need to deserialize it. So in this case, we need to provide the deserializer or the way how the deserialization needs to handled on the Flink side of things. Now, and we have the beginning. We have a source where we need to get data, and this is where actually we start building a topology like data stream API operators combination. So from the source, in this particular case, at the Kafka source, we also define the way how we assign the watermark. We're going to talk about the watermark in different like timing semantics in a few slides. Now, And this is where I'm starting writing my my data stream topology application. So we have a flight events, and the API is also kind of like a similar-ish, following same abstractions that were introduced since maybe Java 8. We can do in Flink, we also can do branching, so we can get the results of send the results on the different streams. This is how we write this back to Kafka. In this case, we're using Kafka Sync and the Kafka Sync because remember we have two topics. We have alerts and statistics. For those messages, we're writing the data to Kafka. Again, we're defining sync, and after that, this sync needs to be attached to this topology somehow. And if I need to do, say, a test, something like this, I'm just using a embedded version. And also, let me see if I use Kafka here or I use embed Kafka here. I don't remember what exactly we're doing there. Yeah, screw this. Let's just run. Let's see how it fails. So now in this particular case, it will run actual Flink instance, but it would be embedded Flink instance. And I believe it uses something like embed Kafka because I don't see anything we started because it failed. Mini cluster is not running yet. It's already has been shut down. Maybe I need to run this with the Gradle. Anyway, we'll take a look after. I know that it runs on CI/CD and it runs successfully. Let me see if I can run this in Gradle Flink processor tasks. See if I run this with build. Where's my other test? Where's the other test verification test? I know that because my integration test should spin off the mini cluster, or I'm yeah, I need to see why it's not starting up. It's green, but my test says like mini cluster is not starting up. So there's a couple things how we can test these applications. First of all, you start the Docker Compose instance of a cluster. There's embedded the mini cluster type of version inside one particular JVM. There is a test containers. There's a library called test containers that allows to use real containers, containerized applications in your testing code. And the cool thing is that it's available pretty much on any language. So if you're using this with Python, you can use, say, Kafka inside the test container and use your real Kafka in your Python tests, for example. Now, once again, to summarize what I just said, it is with Flink. It is much more, it's a real distributed system with all general purpose. There are certain design decisions were made in order to support this general purposeness of this system. For example, comparing to when we're talking about Kafka Streams, two instances of Kafka Streams application, they don't talk to each other. They don't know about existing themselves because they're talking to this consumer group coordinator and the processors that we're getting this metadata. With the Flink, this task managers, and they actually talking to each other. They know that exists. There's like enough resources to distribute jobs and things like that. So this is the real cluster, the distributed system. Now, I mentioned this not once already today. We're talking about stateful stream processing. So state management is very important for these frameworks. How data will be persisted across the restarts of applications, how we can speed up or rehydrate instances of application if they started for the first time. So these type of use cases where we need to find a way how it's done. So in Kafka Streams applications, we use a few interesting things in my opinion. So first of all, when we require having some sort of intermediate state store, when we're using aggregate functions, we are just use APIs. like and the rest of the stuff would be hidden, and we don't need to worry about this since the framework will handle this for us. It will be creating some of the explicit state store. So, but the cool thing about this local state store that will be runs next to your application, it is actually will be replicated for the purposes of failure or disaster recovery in case of failures. So there's a special type of topic called changelog topic that will be capturing all the changes that happens on this local state and propagate this inside the Kafka topic. You will have a special, per particular operation, you will have a special changelog topic inside the Kafka. And when this instance would be killed and needs to be restarted somewhere where you don't have a local storage, so this changelog will be populating this local storage, and the data, your application will start not from the beginning, not from clean slate, but starts with rehydrated state that's ready to use and will be continue appending the things. On the Flink, there's a few things where in Kafka we're storing, in Kafka Streams we're only storing the data that was relevant for our processing thingy. In Flink, we have an ability to have a more broader, or since it's a cluster, and cluster might require some of the maintenance, we can explicitly call and save a save point of if you're running this application or operation that needs to be executed, but you need to brought down this cluster, you can have a save point. You can restart your cluster, and the results will restore from the save point. It will continue from where we left off. And the checkpoints, it's the similar mechanism, but it would happen automatically. With the checkpoints, you can define how often Flink needs to dump these checkpoints into special state, in special state place where this state backend. So in case of, again, failures or restarts, you're running this in Kubernetes, Kubernetes decide to evict one particular pod, this state needs to be rehydrated from somewhere. So, and Flink allows to use local disk. You can attach some of the external storage where you can have a storage of the state. So it provides the way. And usually job manager nothing to do with this. It's only on the task managers. It will be configured, and the task manager will be responsible to retrieving this information. Task assignment scale. So since Kafka Streams has very, like I already mentioned, a very intimate connection with Kafka, it's very much rely on consumer group protocol in the way how assignment is going to happen. Since it is a shared nothing architecture, each individual task that will be executed against one or more partitions, you will not have a task that will be executed, same partitions, because it also will not require defining some sort of lock-in mechanism. If one task needs to perform the computation on other partitions, they will be running in total kind of isolation, and they don't need any explicit logs here. Another interesting thing with it's kind of like a little bit also relevant to previous point about state store. We have state per instance of the task. So each individual, or basically we will have each individual store per partition. You have 5 partitions, so instance of Kafka Streams application will have 5 tasks that will perform computation on top of those partitions. And if you need to use, your the state stores for certain operations, state store will be created per partition. This is very very important to understand in order to understand how to scale those applications properly. Since it is relying on consumer group, you cannot, or you probably shouldn't start more instances than number of partitions inside Kafka. But there's some situations where it actually can be a good idea. In some of the applications that people might have with Kafka Streams, and this is like if you will be looking in the internet and try to find the kind of like a nitpicking about certain problems that Kafka Streams might brought into your life, it is a size of the state. And it is usual complaints and haters of Kafka Streams saying, hey, yeah, but like how to deal with the big state, because if you have a big state, you have a lot of time to when application starts up, because you need to bring all the states into application memory and things like that. There's ways when you kind of like stand up more instances of Kafka Streams application than you need. It's called standby instances, and this instance will not do any processing. It's just sitting there and maintaining state. So in case of failure, it will take over, will continue performing processing, and it also will have a ready-to-use standby state.
Yeah, and that has improved over time, because a couple of years ago, rebalancing a Kubernetes service that wasn't stateful was a nightmare, especially with big tables.
Yes.
Tables. That was a nightmare.
Two great points. If you are running Kafka Streams application in Kubernetes, or probably in most of the cases, you must use something like stateful sets, because of the stateful network identity and stateful disk identity. It would be much more. You will say thank you yourself. Your future yourself will tell you thank you.
Actually, we have ended up offloading all our big state stores to dynamic data tables, to NoSQL tables, and just
for state stores.
Yeah.
Are you writing your own kind of implementation of the state stores?
No, we're just writing a process where we join with a service which actually ends up in a dynamic table. So we join with a dynamic table.
Okay, that's interesting. So there's actually...
That's because I'm storing all the tickets we have sold. So we sell a lot of tickets. So we have like millions of rows. So we're joining them, and that's cost a lot when you're rebalancing.
Yeah, because of the big state, and needs to be picked up by a relevant node.
And Kafka used to when you're rebalancing, Kafka used to say, if sort of say, hey, our production is all limited, all our pods are running, we take another one. And you think about that, because what happens in the old days was that when you introduce a new consumer, all the other consumers say, hey, we'll wait for that guy's ready.
Yeah.
But now it's sort of, now the coordinator says, hey, you guys keep on moving, and the new consumer will take that position.
Yeah, and it will catch up. And also, there's also configurations available in Kafka Stream side of things when the rebalance is happening. In the past, I remember the times when rebalancing is happening, you cannot, obviously you cannot process anything. And the second thing, you will not be able to do access to state store. So Kafka Streams provides the ways how state store can be exposed through some sort of like a REST API or gRPC. So you don't, in case of you dealing with like hybrid world when you have a partially REST and partially Kafka event driven, you can expose the state store in the form of API so other application can query this. So in the past, when the rebalance would happen, since it's a distributed architecture, even the state stores were not available. It will take like a timeout, a very long period of time to wait. Now it's not the case anymore. So now the state stores available for query when rebalance is happening. So which is also pretty cool for smaller like microservices use cases. Yes. Yes, so for Kafka Streams, it uses a small embeddable database called RocksDB, and it will use your file system. On file system, there will be a folder that you define during application startup and configuration where you're putting all these state store files. And these state store files will be stored basically one file per partition per whatever operator will create the state store. It is pluggable. So you can write implementation, your own implementation that use whatever technology you want to use. I've seen people doing this like using Redis as their state store, so they might have a better chance to deal with Redis. But in general, it comes with some already, batteries included, like I like to say.
Okay, a couple of more questions.
Yes.
So one is like, does it Flink supports schema registry?
Well, we can talk about this in short answers. Yes.
Okay. And I forgot. But
Yeah, it will come back to you.
yeah.
So when we look at the diagram of a Flink cluster, we already established that the architecture would be, or like the scalability aspect will be running on top of how many instances of task managers we're going to run, and how many instances of. Let me see if I can quickly find a Flink cluster example. I can show you how it looks like. Oop, that's not slides. Might have like a power flow, but I think it is. And my Docker compose let's see if it's services. TB power flow, no, something else. I don't want to spend the time to find this. I know where to find this. I always have it. Projects, and there's something like Flink, Miller. I think this is it. And and services. Yeah, perfect. That's exactly what I was looking for. So kind of like a tiny Flink project. We're doing up the. So if it's up, let's take a look. Job manager, and we're doing port 8081. So first of all, when our application or my application will be talking to Flink, Flink provides REST API. So you can submit your jar through this REST API, and it will appear here inside these jobs. You will see what kind of jobs are running. Even if you're running kind of like Flink SQL and running some stateful, you will see a statement. You will see this as a running job. This UI also includes information about task managers. So like in this particular case, if I will just do number of task slots, it's kind of like a very small number. Let's see if I can do scale. Okay, if I can do 2 task managers. And it should discover. Now you see I have added another task manager. So now I will be able to schedule more jobs, and I can to figure out how to run this more. In this particular case, my configuration says it has only 2 time slots, or the task slots. And this UI, if you've never seen this before, I highly recommend to play around, because it gives you like very good idea about resource allocation, how much resources one particular operation will take in. When we will submitting jobs. No. Let me see if I will be able to. No, I'm not gonna. So you also inside the task manager or the particular job, you will be able to see the actual topology, like how many messages went through particular operator. So this is quite cool. Let me see if I can run this. Say this application. Build labs. Okay, so if I will go say jobs, submit a new job, I can do this. and we'll go projects. We'll go to Flink. Oh, what happened? You died? What's happened? Submit a new job, add new. Let's do this. We're doing into project. What is happening? I do Flink. I don't know what is happening. Let me do another way around. It's the. We'll take this B. App build libs all. So I'm taking this jar with all my dependencies and stuff, and I will drop in here. So where is it? Okay. Oh, can you not do that? Okay. So this is the job that I submit. I can see what this job will include. It's some sort of like a random generator. I don't remember what this application we're doing, so we're just like I'm just winging here. And when I click submit, I can specify where I can save points for this particular application. Based on different application, you can define this in the different locations. And now I can submit. So job will be running. I will see how they will be executed. Obviously, there's something is wrong, but it's like not the point for this for this demonstration. I can see where the data coming from. I can see how many messages here like went through here and there and stuff like that. And I see many things that can happen with this particular job. Let's see what the task manager will say. Show me what kind of jobs we're running here. Running job. Where is it? Tasks, timeline, configuration. So okay, so it's a kind of like example of like a data generator. It generates some data, submits in Flink, and after that it writes this down in the console. So in this case, I should see something like inside my log, I should be able to see everything that happens. It's no, where's my tasks? Task managers. Let's see logs. Can we see log list? Execution. So on the task manager side of things, also nothing to see. Anyway, so running cluster, scale cluster nodes independently, submitting jobs, looking around what they're doing. They're doing something, so it's cool. It's cool and nice. That's essentially three things that you need to remember from here. Job manager submits a job to task manager. Task manager will be responsible for running this. You can submit this through Java call. You can submit this through REST endpoint. You can upload this jar. And also Flink SQL. I'm not going to talk about Flink SQL today, but it's another way how you can submit a job. Flink SQL allows you writing SQL, and these jobs, these SQL statements will be compiled down to Flink jobs. Dealing with time. Dealing with time in the Kafka Streams and Flink. In the Kafka Streams, we defined a kind of like, we do have a state store that will be represented in the key values. When we are adding a windowed state store, we're adding another dimension. We have a key values, and now each value for these key value pairs will be represented through certain time dimensions. And within this windowed store, we will be able to execute all sorts of things with aggregation. So windowing operations, Kafka Streams, they also support late arriving events through defining grace period of windows. Window can say 5 minutes, but you can have a grace period of 5 minutes as well. So you allow some of the late messages arrive from, it still will be accounted for this time window if they arrived later. Inside the Flink, Flink uses slightly different concepts for dealing with time. It uses concept of watermarks. Watermarks are special type of messages that will be injected into data stream that will be defining like, okay, we start time, all the messages before this watermark, after that closing watermark, and this is how we're gonna be defining our window for our particular operation. There's also ability to handle late events, obviously, because otherwise it would be kind of like pretty pathetic not handling this type of use cases, which are very important. Let me quickly show you how it looks like from perspective of API. So if I would look into my flight delay, flight delay processor on the Flink side of things, we are defining the watermark strategy that will define that bounded out of orderness duration of minutes. We're using a timestamp extractor or timestamp assigner. In Kafka Streams called timestamp extractor. In Flink it's called timestamp assigner. We are reading message, and we're reading this information about timestamp from within of object. Also, we can do this read data from Kafka message, and it's actually two different things in terms of defining time. There's like event time and processing time. Event time when it's something that was either registered inside the event, if you have it like a timestamp, or if you don't have this information, it's also kind of sometimes called log time. When it was written inside the Kafka, Kafka will generate a timestamp when this message was produced into Kafka. This information also can be extracted using the timestamp extractor, or Flink also can understand. Flink being, again, general purpose system, it doesn't know about keys also. So that's why we need to tell, in this, for example, here, we need to specify the key by explicitly tell Flink to use certain keys from application. And now here we define the watermark strategy, so now we can use different type of windows. In this particular case, using tumbling window in 15 minutes, so we want to see how many flights will be delayed, and we will register delay if it took more than 15 minutes to arrive to destination, so we will consider this as late flight. And after that, we do have a processor to process all these things, and we're performing some logic. In this particular case, we're just collecting this information into some aggregated state place. In the Kafka Streams, we do have flight delay processor. The way how the window looks like, we define the strategy for time. So in this case, we're saying that we will want to have windows that we're going to be using in our application within 15 minutes with grace period of 1 minute. All late events arrived after window closed, but we'll give 1 minute of grace. And this window will be moving with 1 minute intervals. The way how I will be using this in my application code, I will be, for example, this is where I start calculating these aggregates. I need to specify the window that I will be using, windowed by this time window. That's how these frameworks handle, like library and framework handle this exactly once. Anyone understands what it means? Exactly once? Who can explain what does it mean?
I guess you mean that one event you are guaranteeing that the event will be processed, but only one time and not twice. And also it will be processed, but only once.
Everyone has the same understanding, or some have a different understanding?
Maybe I can
elaborate
on that. So it no matter how many times, it will make sure that that particular event is there, persistent, irrespective of any fault tolerance or. So if it's same event comes again, it won't rewrite for a case.
This gentleman was more correct to exactly one's definition that everyone is following. And it's actually not funny, because it is it's very common that people think words matter. Words matter, and some people think they know what does it mean. So that's why I decided to, instead of me telling you, I've decided to ask you what you think about this. So you were right when you're saying that it will be processed only once. When your use case is more came from the world of enterprise middleware, MQ systems, and databases, where people were thinking that you produce the message, it stays in message queue and will be consumed. This is what exactly once. It's not correct thinking about exactly once how we think about this in Kafka. It's all about consuming message, processing, and writing back results all in one shot. So there's a difference between produce, store, and after that consume. That's not what we will be talking about. So exactly once in Kafka Streams, it follows. Exactly once was actually implemented in order to stream processing will be reliable. What you were talking more about idempotency, where your producer will write some data in Kafka topic, and in case of failures or some sort of like a network glitches and lights blinking, you will not be introducing duplicates just because you didn't receive acknowledgement from the broker in time. So that's the idempotency where broker would know that if the request came in with the same, we call it epoch, in producer epoch, with the same request ID, it will not try to retry. It will just send acknowledgement back to the producer. Anyway, but this is also a very important component of this exactly once. So that's why it's not called like exactly once processing. It's exactly once semantic. It's the certain guarantees that frameworks like Kafka and Kafka Streams gives to user. I don't want to go into kind of like being a nerd and the talking about the meaning of words. What we really want to talk is how the consumption, processing, and the production back to Kafka will be handled in one. Again, I'm using my words very carefully, in one atomic operation. I'm not saying transactional operation because, again, the word transaction is super loaded as well. So in a book, Kafka in Action, I actually use the example how to implement atomically the financial transactions for certain trades. Because in situation of when we need to deal with the banking account, the balance information, this is something that we cannot modify if we're not certain that everything is checked. For example, we try to execute the trade, but our balance is not doesn't have like a current state. We're thinking that we have money, but we don't have money because there's some other process change this balance. So yes, this use case can be implemented in Kafka Streams, and it's quite elegant in my opinion. Another place where word transaction is actually appropriate is on the producer, because producer can explicitly create a transaction and commit or like produce messages in two topics simultaneously, and you will have a guarantees that after this transaction will be executed and there was no errors, those two messages were successfully committed into two Kafka topics, or three or more. And this, let me a little bit expand on this exactly once concept. So inside my Kafka Streams application, I always have consumer, I always have producer, and I always have some of the processors that will be performing a certain computation, and there will be state store. So my consumer will be reading data that is by default will be committed. So if it will see the topic with the flag committed message, so meaning that it's safely to read this. My processors in my state store execute one particular step of processing, and as a result, we need to write because we want to advance our stream processing, go to the next message. So we need to advance our consumer offset. And we need to make sure that the result of this data also will be written into output topic. So essentially, I can technically extend the transactional boundary to topic and consumer offset topic. And transaction coordinator, it's the some process that will be running inside the broker where producer will be talking to, and this coordinator and producer they implementing like a two-phase commit protocol, and this is where idempotency would be important because these two need to talk and get guaranteed delivery. So it's quite cool, but if you want to use it, you need to. I don't have this slide. Essentially, it's just one property. You're saying enable exactly once processing. That's it. Everything that I just explained to you is to just create additional mechanical sympathy for you, so you will better understand how machinery works. Doesn't anyone know like what's the mechanical sympathy? I forgot who said that, but essentially it was one of the racers. And he was saying that in order for you to be great racer, you also need to understand what is happening inside your car where you're doing certain things. So that's why you need to have a good mechanical background. And you, as a software engineer or data streaming engineer, you also need to have this like mechanical sympathy to this framework. You're probably never gonna use some of the bits that I'm talking about, like explicitly talking to transaction coordinator and doing transaction with producer, but now you understand what the machinery is happening there. So when you will be making certain decisions in order to implement certain pieces of your application, you will be more educated on this concept. So that's why I have these diagrams and I'm explaining how those things are working together. Now, Flink, it's also quite interesting. Again, it's a general purpose system, so they need to come up with framework that would be suitable for any type of use cases, like not only Kafka. And if some of the sources would support this exactly once processing, we need to have these same capabilities in order to the source operator to support this exactly once capability. So that's why they expose certain pieces of API, and usually it will be implemented if Kafka connector says it will support exactly once processing. Most likely exactly once processing will be working exactly as I explained. We read, we process, we submit the data. Things are a little bit complex because we're running in cluster now. So the checkpoint coordinator also will be involved in order to capture this information in case of failures. So in case of successful execution of the thing, so checkpoint coordinator creates a checkpoint as well, and so far so on. So that's why kind of like when you will be checking and exactly once processing is something that you will be care about, you need to check the label on your connector. It's like, okay, so one says, oh, okay, now exactly once supported. So that's how you need to look. I think some Kafka connectors now support exactly once with Kafka, but if you're using other connectors, you need to check if they are supporting this. Now,
sorry, can I ask?
Yes.
There is non-exact ones, like at least ones, at least there's another mechanism, right?
At least and at most.
Yeah.
At most will create you. At most can create you duplicates. At least, it can fail, and you might have some data loss, something like that. With exactly once, is that if it fails, it will retries, and that will try again and things like that.
We'll make sure that recorder or event is there, right?
Say it again.
So it will exact ones will guarantee that that particular event will be persisted, like even if there's any failure.
So in case of failure, nothing's gonna happen. It's like a transaction. It's all or nothing. There would be no. In the past, what might happen is that how you can have at most once. You commit your consumer offset, your application thinks that you advanced, but you didn't commit your actual message to your data, so it got lost somewhere in your application. So you lost this. And the same way applicable with another approach, that you write into topic, but you didn't advance your the offset consumer offset topic. So your application will get back and reprocess one more time. Now you have duplicates in your downstream Kafka topic. Does it make sense?
And of course, you have congestion.
I'm sorry?
You have congestion because if you cannot stack the ones, then you cannot process the events coming after one failing, right?
Yeah.
So
You might have a situation where you need to deal this by implementing so-called like a dead letter queue. You know, if you cannot process, just like, you know, send a message to figure out with this message after, and move on. So in this case, you advanced your like some of the things you cannot recover, like you have a serialization error, where you don't have a schema, you cannot bring the schema from either schema registry or whatever. You have some like technicalities, like some corrupted bytes. So
fortunately, it only happened on that partition, as I recall, right?
yeah, correct. Yes, it's performed on per partition, exactly. Yeah, and to summarize everything what I just said, yeah, cool story, bro. But like what we should use actually. So essentially, if you are looking for like quick framework and you're building microservices, it is something that's quick and easy. You need to have a little bit of flexibility in deployment model, microservice, Docker Compose, Kubernetes, what have you, running fat jar, running the thin jar, running WebSphere, running Kafka Streams inside the WebSphere, maybe. It's also possible. Now, it has a built-in framework for testing. It's great. You can define and test many things without even these things will touch Kafka. There's also like framework called test containers, as I already mentioned. It has, I do have a bunch of examples how to test your Kafka Streams applications with test containers. You don't. It's just out of the box for free. Just saying exactly once, and your processing will be, you know, everything will be handled exactly once. And it is kind of sort of pro and also con in some case. Sometimes people would wish it works, but there's another. If like you can look at this from negative side of things, but I like to be a positive person. From the positive side of things, now you can see there's a plenty of Kafka protocol implementation. There's WarpStream, there's Red Panda, there is a Kafka on Pulsar. They all implement Kafka protocol. So if you kind of running those things, you can run Kafka Streams on top of this. You can run this on top of Red Panda. You can run this on top of the WarpStream. Recently, WarpStream support transactions, so exactly once also possible to do with WarpStream. So yeah, that's pretty cool. Now, where to use Apache Flink? This is the place where you're running big processing shop. You're not running applications. You're building clusters. You're running massive the processing of the massive amounts of data. You have a great experience on kind of like running the clusters. You have experience in running distributed systems. Not only Kafka, you can use connectors. There's even Flink-specific CDC connectors. If you need to capture changes coming from your databases, you don't need Kafka anymore in this case. You can use direct CDC connector for Postgres for Flink. In the past, you would use something like Kafka Connect. Data will land into Kafka, and after that, you can read this in Flink. You can use this with Iceberg, you can use this with other formats, you can use this with whatever files you have on HDFS. It does support schema registry. You can deal with Avro, Protobuf, JSON schema, what have you. I didn't talk about this much, but this is also a very, very important thing to point out. So batch in Flink world is just like a corner case of the streaming use case. It's a bounded stream. So that's why like you can perform not only streaming on Flink, you can perform batch jobs. It's just like simply will perform and will stop this job when the stream will be over. So if you're looking for like a universal solution to replace some existing things that will cover you for future in that's what I like to say. It's not over engineering. We're just simply building for the future. So you can write this, develop same experience writing streaming and batch jobs. Windows, complex Windows operation, late event handling. Flink has built-in framework for complex event processing. Flink has API for Python. Flink has SQL. We're working at Confluent right now to enable integration Flink with AI and how different models can be accessed from within Flink job. Maybe next time if we'll be here, I'll talk about something like this. Yeah, like I said, Flink SQL and FlinkPy. Since Danica mentioned the Iceberg Summit, there used to be one show called Kafka Summit London, but now it's called Current London. And it's not only about Kafka, it's all things in the data streaming world. There's Kafka stories, Flink stories, stream processing stories, Iceberg stories, AI stories, and all the things. If you have the story to tell, call for paper is open until February 17th. And the event is going to happen in May in London. And with this, my name is Viktor Gamov, and as always, have a nice day.